Okay, good morning. So today's lecture is going to be on the BJT based circuits, which are at DC. All right, and we are going to solve some problems. So if you just want to go grab your calculators or use your calculator apps, so you may do so. So far we have learned about the characteristics of the BJT, the internal structure, how it works. We've looked at the forward active mode, we've looked at the saturation mode, we've also looked at the cutoff and the reverse active modes. Okay, so now we are going to solve some problems, and that will give us a better understanding or better insights into both analyzing circuits as well as designing circuits. Okay, all right. So let's try to solve this problem. So we have this BJT with these resistors. The VCC is 15 volt and minus VEE is minus 15 volt. Okay, the base is grounded. Okay, and there is an RC here. This is called RE. Okay, the beta is given to be 100, and the information that is given is for a VBE of 0.7 volt. Okay, the collector current is 1 milliampere. Okay, now the question is, design the circuit so that so that a current of 2 milliampere flows through the collector and a voltage of plus 5 volt appears at the collector. Okay, so this is the question. So first, the question, basically when we say design the circuit, you need to find the values of RC and RE, because those are the two unknowns in this particular circuit. So you have the topology of a circuit, and you have been given the beta value, and there has been some measurement which says that for a VBE of 0.7, you get a collector current of 1 milliampere. Now you need to design the circuit for a collector current of 2 milliampere. Okay, and have a collector voltage of 5 volt. Okay, so let's start solving this problem. So I'll just give you a couple of minutes so that you can try to solve this problem on your own, and then then I will discuss the solution. So once you solve it, please do put your answers in the chat box. Okay, so one of the first things that you can basically do is,
Sir,
okay,
is the
someone has
value of VT given?
VT. Okay, you can take VT to be 25 millivolt. So if it's not given, okay, for any problem, you can just assume that VT is 25 millivolt or 26 millivolt at room temperature. Okay.
Okay.
KT by Q works out to be this value. Yes, RC is 5 kilo ohm, that is correct.
Sir, in the diagram you have said that base is grounded,
Yeah,
then and you say that VB is 0.7 volts. It means VBE, like VB minus VE is the potential at the emitter without the resistance, right?
correct. You're right. So the reason I don't want to solve the problem upfront is that like this will get you thinking and this will help you to develop your problem solving skills. Okay. So please do try to work it out. So finding RC is pretty straightforward. Okay. All what we are saying is this is our VC. Okay. This we want to be plus 5 volt, right? Which means the drop across RC, let me call it VRC, is the drop across RC is going to be 10 volt. Okay. The collector current is 2 milliampere. Okay. So from here you can easily calculate the value of RC to be 5 kilo ohm. All right. This is very straightforward. Okay. The other thing, you know that VB is at 0 volt. Okay. What you need to find out is basically what is VBE for IC equal to 2 milliamp. VBE for 1 milliamp has been given. Okay. You need to find out what is VBE for 2 milliamp. Okay. So how will you find that out? So
It's an exponential equation.
correct. So IC is some IS e to the power of VBE by VT. Okay. So now what you can do is you can take a ratio of the currents. Let's say 2 milliamp divided by 1 milliamp is equal to IS and IS will get cancelled, right? IS will get cancelled. You'll have e to the power of VBE that you need to, let's say VBE2 that you need to find out, which you don't know, e to the power of 0.7 by VT. Okay. Now if you solve this, you will get VBE2. What is VBE2?
Sir, is it 0.717 volts?
Correct. Yeah, some of you might have found out IS from this equation and then substituted and done things like that. It's also okay, but it's always easy to do things easier, right? So you have 2 is equal to e to the power of VBE2 minus 0.7 by VT, right? Let me write it like this: 2 equals e to the power of VBE2 minus 0.7 by Vt. Now you take the logarithm. You have to take the natural logarithm, so be careful about it. Natural logarithm into, so VB2 becomes what? Vt times ln 2 plus 0.7. So let me, this is one answer, this is one answer, okay. So now that you know VBE2, what can you do? You can find out what is VE. What is VE? What is the emitter voltage?
So minus 0.718.
Exactly, because this is at 0 volt. This is basically 0.717, which we have found out. So this is minus 0.718. 0.717 volt. Okay. Now what is the drop across RE resistor?
15 minus
14.28.
What is it? 14 point?
14.282.
Correct. Okay. This is the drop across the resistor. Okay. Now what is the current? What is IE?
1.01 milliamps.
Very good. 1.01 milliamp. How do you get 1.01 milliamp? You have beta.
current.
So you can basically use, beta plus 1 by beta into IC. Right. This is basically beta plus 1 by beta into IC. So you know the current, you know the drop across the resistor. Now it is very trivial to find out the value of RE. Someone had 9.6 kilo ohm. That is not correct. 7.14 also I'm not sure. I don't. That you kind of close, but not exactly. Sorry, 1 second. This is not 1.01 milliamp. Okay, your collector current is 2 milliamp.
Sir, it will be 2.
Sir, your VRE should be 20 minus this, right? 0.71.
Where is 20?
We have plus 5 to minus 15, right, sir? So it should be 20.
No, this is minus
VRE.
15. Minus 15 plus 15. VE is minus 0.717.
No, sir.
Right.
VC is 5 plus 5, right? So from plus 5, we are going to minus 15. So it should be 20 minus the
No.
potential
See,
across.
there is some VCE here. Okay. And this
Okay,
VCE has to be greater than VCE sat, which is around 0.2, 0.3 volt. Okay. In order for this transistor to be in the forward active mode. Okay.
See, sir. VC is. What is VC, sir? Over here?
VCE in this case, once you calculate, you'll find out that it is 5.717.
Okay, sir.
Okay. So emitter is at minus 0.717. VC is at 5 plus 5 volt. Okay. Yeah, 7.07 is the right answer. 7.07 kilo ohms. Okay, is this clear? Like any doubts, any questions? Basically,
Can you explain the question again?
Okay, the question is this. Okay, you have been given a particular circuit, which basically it is a BJT with two resistors, RC and RE. The supply voltages are plus and minus 15 volt. Okay, the emitter, the bottom side is connected to minus 15, top side is plus 15, base is grounded. Okay, now the beta is measured to be 100, and for VBE equal to 0.7 volt, it is found that the collector current is 1 milliamp. Okay. VBE of 0.7 gives rise to 1 milliamp of collector current. Now the question is, design the circuit so that a current of 2 milliamp flows through the collector and a voltage of plus 5 volt appears at the collector. This is the requirement. Okay, so collector voltage is VC. This has to be plus 5 volt. Okay, and the collector current has to be 2 milliamp. When you say design the circuit, you need to fill in all the unknown numbers here. Basically, the unknown numbers here are the values of RC and RE. Okay, finding RC is very simple because VC is given to be 5 volt, and let me just So VC is given to be 5 volt, right? And the drop across this resistor is 10 volt. Then 15 minus 5, and the collector current is 2 milliamp. So that's very straightforward. You find 5 kilo ohm, right? Now basically we need to find out what is the value of RE. Now how do you find the value of RE? You have 0 volt here, that is established. Okay, you need to find out what is the value of VE. Okay, how do you find out VE? You need to know what is the VBE for 2 milliamp current. For 0.7 volt it is 1 milliamp. You need to find out what is the VBE for 2 milliamp. So how do we do that? Basically we take the ratio of the two currents, okay, and you basically calculate what is the VBE2, and that turns out to be 0.717 volt. Okay, now VBE is 0.717, This is 0. So this emitter node will be at minus 0.717. This other terminal of the resistor is at minus 15 volt. So the drop across the resistor is 14.283 actually. And then you find out what is the emitter current. What is the emitter current? Collector current into beta plus 1 by beta, or in other words, collector current divided by alpha. Okay. So you find out IE, VRE and IE is there, you find out RE. Okay. Is it clear to everyone? Does anyone have any clarification, any doubts? I can see that many of you are, yeah, understood? Okay. All right, let's move to the next one. Okay. Now, the same thing. Now, in many of the, so this is like if you take a typical transistor that you buy outside, okay, you can use plus or minus 15 volt. That is like the typical supply voltage. Sometimes you use plus or minus 9, plus or minus 12. I think in the lab, typically we use plus or minus 12 volt. Okay, you can also go up to 15 volt. Okay, now you can do minus plus or minus 9 volt. Now what happens? I just want you to appreciate what happens when you go for a more modern process. What do you mean by a modern process? Okay, of course you'll be looking at the semiconductor devices and so on, like how you have CMOS technology which is being scaled. Okay, even BJTs also sometimes can be integrated along with CMOS. That's called BiCMOS processes, and they were in fact very widely used for RF applications. Even now, some of the very high frequency circuits are done with BiCMOS processes. Okay. Now the same thing, if you were to do it at a different technology node, what happens is VBE becomes higher. Now the supply voltages you cannot have plus or minus 15 volt. Okay. You will see that you have breakdown related issues and things like that. Okay. So the supply voltage will scale down. Okay. When we look at MOSFETs, we'll be talking about the same thing. As you grow in your technology node, so nowadays you will be hearing about 7 nanometer chips Intel is making or IBM is fabricating, and 5 nanometer fab is coming up in by TSMC in the US and so on, right? So what does it mean? It means that the feature sizes are coming down, which means the supply voltages are also scaled down. Okay, when we look at MOSFETs, we'll see that the modern day MOSFETs which you are using in chips, usually now if you see 28 nanometer and below, it will be 1 volt. Supply voltage will be 1 volt and 0. That's it. Okay. So what happens is you have voltage scaling, and also the performance kind of degrades a little bit, which means you need 0.8 volt for a current of 1 milliampere. Okay. Now if you assume the beta to be, let's say, 100 and IC to be, okay, beta to be 100, these are all the given information. So the same question remains. Okay, we need IC of 2 milliamp, okay, VC of 0.5 volt, okay, design RC and RE. Now you should be able to do it pretty fast.
There it will be like 1/10 of the.
No, you can't just like the
RC.
scale. No, you can't scale just like that. RC yes, but not RE. RC because everything just scales the same way.
Yes.
Yeah. Instead of having 10 volt, you have 1 volt. So correct. So which means RC becomes 500 ohm. Correct. You can find out VB2 to be equal to what? VT natural logarithm of 2 plus 0.8. What do you get here? 0.817. Okay. Very good. Now that you know VBE, what is the value of RE?
Sir, 7 kilo ohm.
7 kilo ohm. Can you recheck the answer?
So 338 volts, sir.
You're right. You'll get basically 338 ohms. Okay. Okay. The reason that I kind of did this problem, although it's a little redundant and mundane, is because you should learn to appreciate the fact, or kind of understand the fact that at older technology nodes where the feature sizes, okay, which means that the emitter area, the base area, and the collector area are all bigger. Okay, you can use very large supply voltages like plus or minus 15, plus or minus 12, plus or minus 9, and so on. But once you come to more advanced technologies, of course, the other flip side is like these transistors will be high frequency transistors. Okay, they can operate at much higher frequencies. Now we haven't looked at the frequency response yet, but when we come to that, you will know that these more advanced technologies, you will have better high frequency performance. Okay, and but the flip side is you have to work with lower voltages. Okay, all right. So let's move on. Let's go to another problem today. Okay, now this is a PNP transistor. Okay, this is a plus 10 volt supply. You have a resistor. This is RC. This is a PNP transistor. Okay, and you have VB here, and you have a 100 kilo ohm resistor. Okay, and this is minus 10 volt. Okay, this is 5 kilo ohm. Okay, and yeah, the things that are given are basically, yeah, okay. So this is VC, this is VE. So what is given is the value VB is 1 volt, VE is 1.7 volt. Okay, that is plus 1.7 volt. Okay, and this is the information that is given. The question is, what is alpha, what is beta, and what is the collector voltage? Okay, and
Sir, shouldn't VE be above because the above one is emitter?
oh, I'm sorry. I think you're right. You're right. Yes. Thanks for the correction. Yes. So emitter voltage is plus 1.7 volt. VB is plus 1 volt. Okay, and the PNP transistor, you need to find out what is alpha, what is beta, and what is the collector voltage. Let me just check if RE is given. I'm not sure. Okay, I'm sorry. One more piece of information is that RE is basically 5 kilo ohm. Sorry for missing it out. Yes, this is 5 kilo ohm and 5 kilo ohm on both sides. So I can maybe just give you some hints. Okay, what all do we know? We know that we know the value of VB, we know the value of VE. Okay, so from value of VE, first what we can do, we can find out what is the value of IE, correct? And secondly, we can also find out what is the value of IB, because the base current will flow in this direction.
Is beta equals to 66?
Is it 66? No. Okay, so here VB is 1 volt, which means 1 volt across 100K. Okay, I can see some. Yeah, beta is 165. That is right. Okay, so let me maybe write the answers here. 165 or 166. Somewhere in this vicinity is fine. Yeah, or automatically it follows that alpha is 0.94. Yes, 0.9943. It's okay. I mean, VC, can you add one more decimal point? I mean, like one more significant digit.
Sir, I'm getting exactly 1.80.
Okay, but actually it is minus 1.75. I think the others are also
I'll
getting
check.
1 point. Yeah, you can just check.
Yes.
Okay. Okay, so how do you go about solving this? First, see what all you can find out. Okay, the value of IE you can get directly. How do you get? It is 10 minus 1.7 divided by 5K. Okay, you will get what? 1.66 milliamps, correct? And what is the value of IB? IB is 1 volt divided by 100K. You'll get 10 microamps, correct? Now from these two you can find out IC. What is IC? IC is IE minus IB, becomes 1.65 milliamp. All right. Now you know all these three values. You find beta equal to IC by IB, and then you find alpha equal to IC by IE. Okay. And what is VC? VC is nothing but, what is IC? So IC into 5 kilo ohm. Okay, that is a drop minus 10 volt.
BC is 1.
Okay.
Sir, it
So
should be the other way around, sir.
which one?
No, sir, no, sir. Yes, sir.
Okay, so this is what you would get. Maybe if you're getting minus 1.7, minus 1.8, you can just check if you have made some small mistakes here and there. Okay, whether you took IE value for calculating VC, just make sure. All right. Okay, so any questions, any doubts? Let's move to the next one. Okay, I am assuming that there are no more questions. Okay, all right. So please make sure that you understand what we are doing. If you have questions, please do ask. Okay. So this is a little slightly different way of looking at it. Okay, this particular problem. Okay, you have the values of RC and RE given. Okay, this is grounded. Let's say this is plus 4 volt. Okay, beta is 100. The question is find all the node voltages and branch currents. Basically, find out what is VC, VB, VE. Find out what is IC, IB, and IE. It's pretty straightforward. Okay. Okay, so here there is a trick. Sometimes when you are given exact, see if you, there is one thing that I want you to understand. In some problems, when you are given the value of IC, okay, VBE for a certain value of IC, then you can calculate the exact value of VBE for the current that is flowing. Okay, but what I have given now is more typical about how you would be not only analyzing circuits but also designing circuits. Okay, when you're going to design actual practical circuits which work, lab or in your project or whatever. Okay, you will not know the exact precise value of VBE. Okay, so for all such scenarios, you just take VBE or approximately equal to 0.7 volt and you solve the answer. Okay, so in this case, you have no way of determining the exact precise value of VBE. Okay, it will be somewhere around 0.7 volt. Okay, what is going to change is probably in the tens of millivolt. Okay, your the rest of the analysis will be pretty much accurate. This is how we design practical circuits. You can sometimes you can take it as 0.65, sometimes at 0.6. Whatever you take it, make sure that you specify what you're taking. Okay, and in fact, I think the transistors that we use in lab typically are around 0.6 something. So you can probably take 0.6. In this case, you can just take 0.7. All right. Okay, IC is 1 milliamp. The IC is not 1 milliamp.
Sir, IE is 1 milliamp.
Correct. IE is 1 milliamp.
milliamp. I see.
Correct. Correct. That's right.
Sir, VC 5.3 volt.
Which one? V?
VC.
Yeah, that is right. Let me write the answers here. So we found that IE is 1 milliamp IC is 0.99 milliamp. So what is IB?
9.9 microamps.
Correct. So our 0.01, yeah, 9.9 microamp is also, that's precise, 9.9 microamp, correct. So VC, someone mentioned it is 5.3 volt, which is right, and VE,
3.3.
correct, 3.3. Okay. So basically, how do you solve it? It's quite straightforward. Okay, this is 4 volt. This is what you would pretty much do in most of the problems. Basically, this is 0.7 volt standard. Okay, so what is the value voltage at this particular node? This becomes 3.3 volt, right? So 3.3 volt divided by RE is RE of 3.3K becomes 1 milliampere. Okay, so beta is 100. So which means that IC can be written as what? Beta divided by beta plus 1 into IE, which becomes 0.99 milliamp. Okay, so IC value is also known. Now IB can be written as what? IC by beta. Okay, or it can also be written as IE divided by beta plus 1. Both cases you end up with 9.9 microamp. Okay, now that you know the current through the resistor RC, okay, VC can be written as what? 10 minus IC into RC. Correct? Okay, so it's
Sir,
fairly
IC, sir,
yeah.
IC plus IB is equals to IE, right?
Correct. You can do that also.
So
IB can
why
be
did we get 9.9 microamperes? You should get 0.01, right? Milliamperes or 10
okay.
microamperes.
Approximately the same.
What is this? 9.9 microamps can be written as very close to 10 microamps.
So it will
Just
be
an
IE by
numerical
beta,
approximation.
right? If
It
you
is
take IE by beta,
IE by
means
beta plus 1.
Yes, sir.
Okay. Yeah, I mean 9.9 and 10 microamp, like, see, as circuit engineers, you don't chase after these 0.00 stuff. Okay.
okay,
Yeah, it is like, see, when you start actually building circuits, okay, there is a limit to which you can actually measure things. Beyond that, there is that level of uncertainty. Even this circuit, when you actually implement, okay, you will not get precisely 3.3 volt here. Why? Because we have just taken it to be 0.7. Okay, it can be 0.71, 0.72, 0.69. Okay, somewhere in the thereabouts. RE value will not be 3.3K precisely. It will be slightly different. RC will not be 4.7K. Okay, it will be slightly different because of the tolerances. So you'll have, if you take this exact circuit and implement it in your lab, okay, in a breadboard and connect these voltages, you will see something which is kind of in the same range, okay, plus or minus some amounts. Okay, so that always we should understand.
Sir,
Yeah.
sir, can you explain I equal to 1 milliampere hour?
IB equal to which part? Which part?
I first part, sir. I equal to 1 milliampere hour. Is there
10 micron. This part is it?
no, no, sir, no. I equal to 1 milliampere.
IE equal to 1 milliampere. Okay, okay. That is simple. See, what we are doing here is, let me just change to it. See, this particular node is at 4 volt. Correct. And we say that nominally this transistor, because in the previous, I think the first problem that we solved, we had the information with which you can calculate the precise value of VBE. Okay, you said for 1 milliamp you have a VBE of 0.7, and for 2 milliamp it becomes 0.717. Okay, but here you don't know, and this is mostly the case that you have in a practical scenario also. You don't know what is exactly the value of VBE. It will be nominally around 0.7. Okay, so what you do is you solve the circuit taking a nominal value of VBE. So if this is VBE, what will be the voltage at this emitter node? 4 minus 0.7. You get 3.3 volt. Okay. Now this 3.3 volt is across this resistor of 3.3K. Okay. So V by R gives you the emitter current. Clear?
Clear, sir. Thank you.
Okay, good. All right. So now I'll give you a small twist. Okay, same circuit, 4.7K. Let me see who is able to catch it. Okay, same kind of circuit, 3.3K here. This is grounded. Okay. Yeah, sorry about that interruption. I had to. Yeah. Okay. The difference in this circuit is it is plus 6 volt. There's also another difference. The beta is 50. Okay. Now same thing. Find out all the node voltages. I'll just say find all voltages and currents in this circuit. Okay. There is a twist in this problem. Okay. So let me see who is able to find it. So it's just running out of time. I think it's just about 11:45. What is the value of VE?
Actually, the maximum current that can go.
Sorry, come again.
5.3. 5.3.
Yeah, 5.3 volt. Okay, very good. So what is IE?
1.606 milliamps.
1.6 milliamp. Wonderful. Okay. Up to here things are fine. Let's look at the twist part. Okay, what is VC? Sorry, what is before that? Let's say what is IC?
1.5.
Okay, 1.77. Okay, milliamp. Okay, what is VC?
2.6.
2 point?
2.6 volt.
2.6 volt. Okay, so now you look at this value. Okay, so I want you to pay attention to, do you think that this solution is correct?
No, sir.
Why?
No, sir. Because VC is the lower.
VB would be greater than VC here.
Sir, VC is a lower potential, sir.
Exactly. So if you look at VC, the value of VE, and of course VB being at 6 volt, okay, so this solution does not exist, which means what? The VBE is, the first junction, emitter based junction is forward biased. This is no problem. What about the collector based junction?
Power bias.
Correct. Right? So, which means, is this in the forward active mode or some other mode?
Saturation.
This is in the saturation mode. Okay. So, basically, you would have calculated IC by using the beta equal to 50. So, if it is saturation mode, beta equal to 50 does not work. Correct?
Yes, sir.
Okay, so which means that this solution is not correct. Alright, so it is obvious that if you assume a forward active mode, this solution is not, if you assume a forward active mode, you are not able, the solution is invalid. Okay, you assume that it is a forward active mode, but when you calculate, you find out that it is not in the forward active mode, which means your assumption is wrong. Okay, it turns out that it is in the saturation mode. Okay, so how do you solve problems when they are in saturation? Typically VCE saturation is around 0.2 volt. Okay, so which means this voltage is 0.2 volt. Now what will be VC? Now just like how we take VBE to be 0.7 as the nominal value, you can take VCE saturation to be 0.2 as the nominal value. Yeah.
5.5.
It will be 5.5. Correct? Very good. Now if this is 5.5, what is the value of collector current?
N minus 5.5.
Exactly. So what is the value?
0.957.
0.95.
Okay, some 0.96 milliamp.
Yeah.
Right? Okay. Okay. Now can you find out what is IB? IB can be written as what? IE minus IC. What is the value of IB?
0.64.
Okay, 0.64 milliamp. Alright. Now can you calculate what is the beta forced here? IC by IB?
1.5.
1.5. Okay, so this is how it happens. Sometimes it is always fine to start with the assumption of a forward active mode, but many times it might turn out that your assumption is not correct. Okay, sometimes. Okay, so depending on the values, both when you are designing things as well as when you are analyzing circuits, either practically or in problems that you solve or in simulation. Okay, so in that case you cannot apply this formula that IC is equal to beta by beta plus 1 times IE and so on. Okay, so that solution will be wrong. Okay, so here it is in the saturation region. You assume a saturated voltage and then you calculate. Now the interesting thing here is basically that the value of IB is much higher than what you got in the previous problem, right? Same resistor values, the beta value has changed, but then what do you see here? You have around 10 microamp of current here. What happens in the saturation region? You have 640 microamps of current. Okay, so typically in saturation region your IB increases a lot and your IC by IB ratio is smaller, and nominally you assume 0.2 volt as your this thing. So any doubts, any questions?
No, sir.
Okay, is it clear? Okay, thanks everyone.
Can you repeat once a little bit, sir?
Yeah, sir. Can you please actually
Okay,
Right.
okay. So
how to
what
catch
we,
it if it is in like saturation?
right. So the way we did it was basically we assumed that it is in the forward active mode. That's what we did for the first 4 problems that we solved in today's class, right? And we went ahead and we solved it, and we found out that VC is 2.6 volt, which is lower than the emitter, and also which is lower than the base voltage. Okay, so which means that the collector base junction is forward biased, which means that our assumption that that this particular transistor in this circuit, okay, is in the forward active mode is a false assumption. Okay, we saw that the consequences of this is not matching. There is a contradiction. Okay, so our assumption is wrong. So what we need to do is we need to understand that this transistor is not in the reverse active mode also, because this junction is forward biased, right? And it is not in the cutoff mode also, because some current is flowing. This is forward biased. Okay, so the only other option is saturation mode. So if it is in the saturation mode, what happens? This beta value, so IC to be calculated, what would you say? Usually you would have written as let me use this color only. IC is equal to beta by beta plus 1 times IE. Okay, so this formula does not work. Okay, so you need to you have a beta forced, which is different. Now how do you find out, how do you solve the circuit? You assume that, you don't assume, you realize that the circuit is in saturation mode, and because of that the VCE is equal to VCE saturation, which is 0.2 volt. Okay, which means the V collector to emitter voltage is 0.2 volt. Okay, now we found that this voltage is what, this particular voltage is at 5.3 volt. So automatically this is going to be at 5.5 volt. Now once you know this, you can find out what is the collector current. From here you can find out the emitter current and the beta forced values. Okay, is it clear? So typically while solving these types of circuits, whether you're analyzing an actual circuit which you find in the internet, you try to find out the currents, or whether you're designing your circuit and you want to know what is happening, or whether you're designing a circuit to be implemented in the lab practically, you assume that it is in the forward active mode, because that is, for all amplifier purposes, that is the region in which you want the transistor to be in. Okay, but then like in this case, if you find that, let's say you're designing a circuit, okay, and you have designed it and you end up with these values, when you analyze it, you realize that you made some mistake. Okay, what will you do? You will go back and change something here such that this transistor goes into forward active mode and not into the saturation mode. Okay, is it clear?
Yes, sir.
Okay. Okay,
So
then.
one more.
Yeah.
So always assuming that VBE is equal to 0.7 volt, is it like correct? Like
Yeah.
always take boundary
Correct.
values.
Like sometimes you can see, sometimes you can say 0.6, sometimes 0.65, depending on what you are getting. Okay. If you see in yesterday's class, I was showing you the data sheet, right? Let's say you are using the BC547. You will see that the voltage range in which the currents are happening is around 0.65 or something. So then if you are using that transistor to design your circuit, you can just take 0.65 and design. Okay.
Sir, I have small doubt, sir.
You can take a higher value too, na? Like 8.8 volts or something like that. So will it affect the circuit?
You want to change the supply voltage.
No, sir. So I'm saying that whenever we are solving such problems, we always assume that VB is equal to how much we need for it to be in the forward bias. Okay, so we take it at 0.7 or 0.6 like that. But for it to work in forward bias, it can take even higher values. That I'm. How are we assuming this?
Yeah, you can. That's a good question. So let me. Yes. Okay. So if you look at the IC versus VB curve, how did it behave? It was something like this, right? No, something like this. Okay. This is your diode response. Now the thing is, this range is typically let's say 0.7. Now your question is, what happens, let's say this is 0.75 and let's say this is 0.8. Okay, your question is, what happens if I overdrive it? Okay. Now what will happen? Yes. If you look at this response, okay, it's kind of going beyond the screen. Now, assuming that breakdown and other things don't happen, just for a moment, just assume that it can give limitless amounts of current. Let's say this value is some 1 milliamp and this is some 10 milliamp, and somewhere here is 100 milliamps and so on. Okay. Now at 0.8, let's assume, okay, your IC becomes some 1 ampere of current or something. Okay. Now what is the problem? If you kind of extrapolate this curve, let's say at VBE of 0.8, you're getting 1 ampere of current. But for this transistor, let's say the IC max is 100 milliamp. That's what we saw in the data sheet yesterday, right? And yesterday and also in the previous class. So what will happen as you keep increasing VBE, as you go beyond, somewhere in this region, okay, your transistor will burn. Okay?
Yes, sir. Yes.
This is what happens.
So a typical transistor doesn't like allow it to have like a large range of like VB values.
Yeah.
That's what
So the voltages across the base emitter junction is typically restricted to just some small changes across around maybe 0.6 or 0.65 or 0.7, something like that, which is why we just take that to be the nominal voltage and solve or design circuits. Okay. Now, as I mentioned, I think like how we saw in problem number 2, we saw that in this particular technology you have 0.8 volt giving you an IC of 1 milliamp. Okay, so that happens. Okay, if you are working in such a technology node, then obviously you will have such restrictions. Okay, and also there are transistors which can handle 1 ampere of current, 10 amperes of current, and even much more. Okay, or especially power electronics transistors which are used in power electronics can easily handle such very high voltages. Okay, a very
In
high
that
current.
case, can we supply VB of greater than 1 volt?
It depends on the transistor. Okay, you have to look at the data sheet of the transistor. Right now, what we typically use for normal applications is something like this. This is what you'll be using in your lab also. This is what you'll be typically using when you're using your in your projects also. Okay, there are some specialized devices for some specialized purposes for which you need to consult the data sheet and then find out what will be the nominal voltages. Okay. Okay.